Okay, so we are recording now. Well, so we have reached section 8.5. We're going to talk about power series today. And you actually in your homework in the past had seen a power series. It was a very simple power series, but now we're going to go over it in more detail. So far in chapter 8, you have learned about different types of, well, you first learned about sequences, and then sections 8.2, 8.3, and 8.4, you learned about different kinds of series, and you've learned about tests that tell you if a series can converge or diverge. So like, for instance, you have the comparison test and the limit comparison test. And then, of course, if your series has positive and negative term, not positive and negative terms, you have an alternating series test. And then you have the ratio test for absolute convergence of a series. So you have really a lot of concepts that you learned here to help you determine if a series converges or diverges. Now, ultimately, what we want to do is to be able to take a function and represent it as a series, and that would be what we call a power series. So that we're going to learn, when we get into section 8.6. But for now, let's focus on a power series and what is officially a power series. So, a power series is a series of this form. Okay, you see it all highlighted here. This is called a power series. So power series has a variable x in it. Power series has a variable x in it, and it's the summation of terms of a series where every term, well, you have the c sub 0 plus c sub 1 times x plus c sub 2 times x squared, and so forth. The c sub n's are constants, and they're called the coefficients of the series. And for each x, the series becomes a series of constants. In other words, if we were to pick a value of x and substitute it in that power series formula, then we would get a series that we can test for convergence or divergence. And a power series may converge for some values of x and diverge for other values of x. So that's what a power series is. And the sum of the series is actually then a function. So you see, let me just highlight this, move this up a little bit. The terms of the series involve the variable x. So you can think of the infinite series, the power series, as a function of x. And that's what they're showing in the highlighted box. And the domain of the function is a set of all x values for which the series converges. So like, for instance, you're going to learn, for instance, that you can take the cosine function, and you can write the cosine function as a power series. And there's an interval of convergence for that is actually all real numbers. But other types of functions, when they're written in as power series, their interval of convergence would be maybe more restricted than the function's normal domain. But what I'm really getting at here is, if we're going to write a function as a power series, then that power series representation of the function is only good over what's called the interval of convergence. So they talk, for instance, like, let's say you were to let c sub n equal 1. Let's say you were to let all the coefficients of the power series equal 1. Well, if you did that, you would get this power series here, right? That's where all the coefficients are equal to 1. And that power series should be recognizable as a geometric series with a common ratio of x. Okay, so that power series there in the highlighted gray box, 1 plus, it's 1 plus x squared plus x cubed, and so forth. That is a geometric series with a common ratio x. And it converges when the absolute value of x is less than 1, or when x is between -1 and 1. And that power series would diverge when the absolute value of the common ratio is greater than or equal to 1. Okay. So, that was a very simple power series, and we were able to use our knowledge of geometric series to determine an interval of convergence. But of course, in our types of problems, we have, we have all different kinds of power series. So let's go ahead and look at one in the notes here and determine an interval of convergence for this power series. So one moment, let me bring it up here. Yeah, this power series here. So take a moment, copy it in your notes. Okay, so this series, this is our power series, and with power series, let me just get my font adjusted here. Yeah, so with power series, okay, and we can write out some terms for the power series to make it a little more, just so you can see what the series looks like. But we're interested in finding an interval of convergence. An interval of convergence are the allowable x values over which the power series converges or has a finite sum. And once we find the interval of convergence, we look then for, we determine quite easily what the radius of convergence is. So just so you can see what this power series looks like, I'm going to write out the first 3 terms for you. So that's on the next page here. Okay, so I wrote out some terms of the power series. Let me give you a moment to copy here. Okay, so let's see what we have here. So When n equals 1, you get the first term. When n equals 2, you get the second term. When n equals 3, you get the third term, and so forth. So we write out then the first three terms of the power series. And, we just to give you an idea, to make it a little more concrete, what this summation means. It means add up these terms, and we find the terms by letting n go through 1, 2, 3, 4, and so forth. We wish to know for what values of x this power series converges. So whenever we want to find out about convergence of a series, we have to resort to some kind of test to help us. So you've learned a lot of tests. You've learned a lot of different convergence tests. And section 8.4, there was a test that we used that was used to determine convergence of series where the terms are a little bit maybe difficult to analyze using some other tests like comparison tests and so forth. What's the test that the test I'm talking about? It begins with an R. Section 8.4, you learned about that's right, the ratio test. That's right, Mario. You learned about the ratio test. So the ratio test is actually the test we're going to use here to help us. All right, let's remember what this is here. So this is our series, right? And let me just the terms of your series are a sub n, right? So the nth term of the series. So the nth term of this series is -1 to the nth power times n squared times x to the nth power divided by 2 to the nth power. So we're going to use the ratio test to try to help us determine values of x for which the power series converges. Are there any questions so far? Okay. Okay. Well, let us move on then. So, all right. Here's the nth term of the power series. And we use the ratio test. So the ratio test says, look at the ratio of the n plus first term to the previous nth term. Take the absolute value of that ratio and examine the ratio as n goes to infinity. Find the limit of that ratio as n goes to infinity. And that's what I'm doing here. So let me give you a moment to, I kind of want to make sure that when I'm talking that at least you've copied down what I'm talking about. So let me give you a moment here. Okay. All right. So, so here, this is the nth term. And to determine the n plus first term of the power series, which is this term here, we substitute for n plus 1. So everywhere in the nth term, here that we have an n, we substitute in for n plus 1, and that'll give you the n plus first term. But now what we have is we have a fraction divided by a fraction. So you learn that when you have a fraction divided by a fraction, you could compute that by taking the first fraction and multiplying by the reciprocal of the second fraction. So if we do that, then, okay, here is then that step. I took the first fraction and multiplied by the reciprocal of the second fraction. Well, I have to compute this ratio. I have to simplify this expression, so it makes sense to group like terms over each other, right? So, I mean, that's what I do in this step here. I just group together like terms, and then I simplify. I simplify everywhere. And then that gets me this limit. So the limit as n goes to infinity of the n plus first term to the nth term is equal to this limit here. Are there any questions on that? On the math that you see there? Okay, all right, well, let us proceed on here. So what happens to -1 to the first power when we take the absolute value? What's that going to become? The absolute value of a negative is a positive, that's right. So, I mean, it's not positive yet, but it's going to become positive. So I guess maybe what I'll do is, hold on, I have an idea. So, hold on, let me just, I want to give myself some space here. Okay, so that's fine. Now, something stays in the absolute values and something can be factored out. Okay, could I bring out the 1/2? I want to say this the right way. No, hold on. Let me be more precise. Hold on. Here's what I'm trying to say. Could I rewrite this limit like that? In other words, the n plus 1 divided by n quantity squared. Okay, Nathaniel, I brought that out in front of the absolute value. Why can I do that? Why can n plus 1 over n squared, why can that be brought out in front? That's exactly right, Nathaniel. It'll be always positive. It's always going to be positive. So you can factor that out of the absolute value. And of course, the negative goes away because you're doing an absolute value. Now the x there, this x, hold on, let me make this a little, yeah, this x here cannot be brought out of the absolute value sign because x could be positive or negative. It's a variable. It's a variable, so we're allowing it to be, you know, any number. Now that doesn't mean that the power series would converge for any x value, but we can't bring the x value outside of the absolute value like we could the n plus 1 over n squared. So all right, let's go to the next page. If we're good with this, let's continue simplifying this. So I put in an extra step here. So, but that we get to here, right? We get to here. And n plus 1 over n, remember, is like n over n plus 1 over n squared. And that gets you 1 plus 1 over n squared. As n goes to infinity, 1 plus 1 over n goes to 1. So you get 1 squared times the absolute value of x over 2, which is the absolute value of x over 2. We're using the ratio test here. So by the ratio test, the power series will converge for x values when that common ratio L. I want to say the L is when you take the limit of the ratio of a term of the series divided by its previous term, and let n goes to infinity. I want to say this the right way. If you have a term of the series and you divide it by the previous term of the series, as n gets large, the ratio of those terms is going to approach a common ratio L. And that common ratio is the absolute value of x over 2. Well, if the power series converges, the ratio test says convergence occurs when that ratio L, or that limiting ratio L, is less than 1. So that's how we're going to that's how we're going to find out the values of x for which the power series converges. We have to solve an inequality. The inequality we have to solve is the absolute value of x over 2 is less than 1. Okay. Are there any questions? All right. Well, so let's go to the next page here and solve this inequality. Well, actually, let me go to the whiteboard real quick. So what we have here is the absolute value of x over 2 is less than 1. That's what we want to solve. So let's just, okay, let's take a little analogy here. Let's say you had the absolute value of a is less than 1. Okay, and you drew a number line here. Here's a number line with a values, and here's some a values. Okay, and on the number line, what graphically would the a values be that such that the absolute value of a is less than 1? What on the number line would graphically be the set of a values that satisfy that inequality? That's right, Nathaniel. It's going to go from -1 to 1, open interval. So when we say the absolute value of a is less than 1, the absolute value of a less than 1 means that a is less than 1 and greater than -1. Okay, how many remember doing these kind of inequalities, maybe in high school, or seeing these kind of inequalities before? Maybe you have, maybe some students likely would have. All right, let's say you have the absolute value of cheese less than 1. If the absolute value of cheese is less than 1, then what would cheese be between? Right, it would be, that's right, Tosh, it would be less than 1 and greater than -1. So when we see this inequality, absolute value of x over 2 less than 1, think of x over 2 as like a piece of cheese. Okay? So this here, if the absolute value of 2, absolute value of x over 2 is less than 1, this means x over 2 would be less than 1 and greater than -1. And so I just wanted to kind of review these absolute value inequalities so that now when I go to the solution, you'll understand. So okay, let me get back to the solution here. Okay, so we want to solve the absolute value of x over 2 is less than 1. And here we say that, okay, well, if the absolute value of x over 2 is less than 1, then x over 2 is greater than -1 and less than 1. And let me see here. I can probably put in a little step here. So one moment here. So x over 2 less than 1 greater than -1. What we can do is we can multiply through by a 2, right? And that'll give you -2 is less than x, which is less than 2. Because the 2's cancel out. And so that gets us here. And incidentally, the inequality signs don't switch because you're multiplying through by a positive 2. So this tells us then that our power series will converge when x is between -2 and 2. our power series would converge. So like for example, and let me just I'll come back to this, don't worry, but I want to go to the whiteboard real quick to show you something. So like for instance, okay, here's our power series. It's an alternating power series, right? And if X were equal to 1, then, I mean, if we just decided to substitute in an X value of 1, hold on. Okay, then our power series would become just a regular series. Okay, like it's not a power series anymore because there's no variable X. We're letting X equals 1. So if X equals 1, then you see how I'm substituting a 1 in for X here. And 1 to the nth power is just 1. And so the series becomes this series, and that series is going to converge. It converges because the X equals 1 is within the convergence zone, right? We said if X is between -2 and 2, the power series converges for those X values. Now, on the other hand, if X were equal to 3, then your power series would diverge. Well, I want to be a little careful here. So far, based on the information, and in fact, it's going to be the case. 3 falls outside these allowable X values. So I'm just trying to make this a little more concrete for you. Okay, when X equals 3, power series diverges, or the series diverges. Okay, so but the question always is, well, Dr. Duty, we know we have a range of X values for which our power series converges, but could there be any other X values out there? I mean, the X values are like the whole real number line, right? Could there be any X values out there where the power series converges? Okay, so that being said, well, let's go back to the solution here. Because remember, what about the endpoints? What about the endpoints of the interval where X equals -2 or +2? Well, if we try to use a ratio test, the ratio test would just give us a 1 if we substitute in -2 or +2. Okay, so like we know the limit, we know the limiting ratio is the absolute value of x over 2. So if we were to put in -2 for x, the absolute value of -2 over 2 is the absolute value of -1 is 1. But the ratio test gives no information when we get a ratio of 1. It just gives no information. So we can't use the ratio test to determine if the power series converges at the endpoints -2 or 2. We have to manually then check if the power series converges at those endpoints. You have to do a manual check, and I'll show you that. But how many, just out of curiosity, when you worked on the section 8.4 homework, maybe tried using the ratio test and you got a ratio of 1 in the limit, and so the ratio test was uninformative? That usually happens to students because they try to overuse the ratio test. Did any of you experience that when you worked on the section 8.4 homework? Okay, and should happen to you. Okay. All right. All right. Well, so let's test the series out when x equals -2 or +2. Let's test them out. So we go to the next page. Are there any questions before I move on? Okay. Well, all right. So here is when x equals -2. See, we substitute in -2 into the power series, and we do some simplifying, and we end up getting a series that diverges, no question about it. Let me give you a moment to just copy down what you see there. I think it's pretty straightforward, the math. The negative -1 to the nth power and the -2 to the nth power. Okay, I put those together here, but -1 to the nth power times -2 to the nth power is -1 times -2 to the nth power. That's that rule, if you have A times B to the nth power, that equals A to the nth power times B to the nth power, right? How many remember that rule, maybe from their high school days, learning that rule? Sure, Tosh remembers that. Absolutely. And that's all we used here. Because we have to, in order to know what our series looks like at x equals -2, we have to simplify the series, and that's what we do. And we end up getting a series that diverges by the test for divergence, because the terms of the series are not they're not approaching 0. Although we know that just because terms of the series approach 0 doesn't mean the series is going to converge. But if the terms of the series do not approach 0, then you know the series is going to diverge by the test for divergence. Now, what about when x equals 2? What about when x equals 2? Well, when x equals 2, okay, this is what the power series becomes. So here, I'm substituting 2 in for x, and we get some simplification here. 2 to the nth power simplifies out with 2 to the nth power. And again, we get an alternating, well, here we get an alternating series, but the terms aren't dying down. So that series will also diverge. So our interval of convergence is going to be and I'll show it on the next page, but the interval of convergence is going to be the open interval from negative 2 to 2. The endpoints are not included here. And in your homework in WebAssign, which will you have, I believe, about 14 questions. The one that's due on this Thursday. You're going to have problems where, I mean, you're going to have to find the numbers that make up the interval, and then you got to decide if the endpoints, is it an open interval, is it a closed interval, is one side open, is one side closed, and that's a very important part of the problem. All right. Are there any questions before I move over to the next page to summarize this example? Okay. Well, so in summary then, the interval of convergence of our power series is the open interval from -2 to 2. And what I've done here is I've drawn on the number line just a picture of the interval. Now, the radius of convergence is if you take the length of your interval and divide it in half, or divide that length by 2, you'll determine your radius of convergence. So this interval of convergence, which goes from -2 to +2, what's the length of that interval from -2 to +2? What's the interval's length? That's right, Tosh, 4. So half of 4 is 2. So the radius of convergence is r equals 2. Okay, I'll give you a moment to copy that. Okay, so I want to look at a problem from the textbook. Uh, we'll, after this problem, then we'll take our classroom break, but I want to look at example 1 from the textbook. Let me bring up the book. Where is that? Ah, here we are. Okay, so example 1 talks about a power series that converges only at its center. In other words, it converges at just one value of x. And here below, they show the ratio test, and you'll notice that this power series has a factorial in it. It has a factorial. So what I'd like to do is I'd like to just reemphasize the computations you see here in example 1. So I'm going to go to the whiteboard. I want to just go over that with you. So this here is again, it's example 1 from section 8.5. Let me change that font a little bit here. And the power series is this power series. This one starts at n equals 0. So n factorial times x to the nth power. And we're going to use the ratio test. So we take the limit as n approaches infinity of the n plus first term to the nth term. Now the nth term is the term you see right here, right? This here is your nth term. So that's just n factorial times x to the nth. To get the n plus first term, we'll just replace n with n plus 1. Okay, so this is the ratio test. So sometimes students have difficulty simplifying out factorials. Well, if you had, like, for example, let's say you had 4 factorial. 4 factorial is 4 times 3 times 2 times 1. And then let's say you had 5 factorial, which is a 1 factorial higher. Kind of like here when we have n factorial and n plus 1 factorial. Well, 5 factorial is 5 times 4 times 3 times 2 times 1. But we can think of that as 5 times 4 factorial. See that? So that's very handy, that understanding that, because we can utilize that over here for our ratio test. I'll leave n factorial alone, but the n plus 1 factorial, the n plus 1 factorial, I'll write that as n plus 1 times what? That's right. Good, Tosh. N plus 1 times n factorial. I mean, it's okay to do that, and it's nice to do that because look what happens. Look what happens to the factorials. Let me take off my email. I don't want any emails interrupting the lesson here. The noise. So see, the factorials simplify out, right? And so what you're left with then is you're left with, hold on, I gotta get that. So I changed the font size. All right, that's good. That's good. That'll work. So we're going to get here the absolute value of n plus 1 times what? What is x to the n plus first divided by x to the nth equal to? X to the n plus first divided by x to the nth. What do we do with the exponents? That's right, Ange. We subtract the exponents. And so you get x to the first. Now the n plus 1 can be brought out front of the absolute value. And so you get, in the ratio test, you get the limit as n goes to infinity of n plus 1 times the absolute value of x. What's that going to equal? So x is like a some fixed number, but n plus 1 goes to infinity. So that's right, Tosh. That's going to equal infinity. Okay, infinity for all x, except x equals 0. If x equals 0, then you'd have infinity times like actually 0. You'd have n plus 1 going to infinity multiplied by an actual 0. And that's not indeterminate. That equals 0. So this power series here, okay, this power series here converges at one value of x equals 0. Okay. Are there any questions on that? All right. So that being said, then, if we go back to example 1 in the book, now what you're seeing in this example should make good sense. The ratio to the series diverges when x is not equal to 0. Okay, that's in the pink banner down there, the highlight. By the ratio test, the series diverges when x is not equal to 0. And the series converges only when x equals 0. Okay, so there, now you've seen two examples. How many at least initially feel reasonably comfortable with what you're learning in section 8.5? How many of you are at least somewhat comfortable? Okay, Taj is good. So that's one student. All right, Nathaniel is reasonably comfortable. Okay. All right. Well, good, good. And it'll take a little practice. So, are there any questions before I stop the recording? Who's feeling good? Give me a thumbs up if you're feeling good so far. Okay, Angie is good, and Jan is good. All right, very good, very good. All right, well let me stop the recording here, and I'm going to give you some time to work on your new assignment. I'll stop the recording.